Good morning, everyone. My name is Dhruv, and today I'll be discussing our project on applying Q-learning, a reinforcement learning technique, to the classic Snake game. This project explores AI's potential in game playing and autonomous decision-making systems. The classic Snake game, where the player navigates a growing snake to eat food while avoiding collisions with itself and the game boundaries, serves as the foundation for our exploration into reinforcement learning. By applying Q-learning, we've enabled the snake to autonomously make decisions that enhance its performance over time without any predefined strategies or paths. We selected this project to showcase how Q-learning can effectively navigate challenges in a dynamic environment like the Snake game. Beyond gaming, the principles of AI demonstrated here apply to real-time decision-making in areas such as robotics and autonomous vehicles. This exploration thus not only advances our understanding of AI in interactive applications, but also illustrates its broader potential in adaptive learning systems across various fields. Let's explore Q-learning, a key model-free reinforcement learning algorithm that teaches agents to perform optimally by learning from the outcomes of their actions. Unlike model-based approaches, Q-learning doesn't require knowledge of the environment, making it ideal for complex or unpredictable settings. What is Q-learning? Q-learning uses a Q-table to track Q-values, which estimate the total expected rewards an agent can achieve by starting at a given state and taking specific actions. This table updates as the agent interacts with the environment, providing a record of state-action pairs. How does Q-learning work? The Q-learning process starts with an initially arbitrary Q-table. As the agent explores the environment, this table is updated using the Q-learning formula, refining the agent's decisions based on observed rewards and leading to optimized behavior over time. The formula is as follows. S is the current state. A is the action taken. R is the reward received after taking action. S dash is the new state after action. A dash are the possible future actions from state S dash. Alpha is the learning rate, determining how much new information influences the existing Q-value. Gamma is the discount factor, which weighs the importance of future rewards versus immediate rewards. The objective is for the Q-values to converge to stable values that provide a strategy for the agent, a guide on what actions to take in various states to maximize rewards over time. Q-learning adapts to various environments by learning from rewards, useful in scenarios from gaming to robotics and finance. It evolves from exploring new actions to exploiting known strategies to enhance performance, demonstrating the importance of balancing these elements for effective learning. In our adaptation of the classic Snake game, we've introduced several modifications to the traditional gameplay to create a more complex and challenging environment for our Q-learning agent. The game is set on a fixed-size grid, where the snake navigates to consume food items that appear in random locations. Each time the snake eats, it grows longer, which progressively increases the difficulty of avoiding collisions with itself or the game boundaries. To enhance the complexity, we've added multiple food items that can appear simultaneously on the grid. This not only increases the strategic depth of the game, but also forces the agent to make more complex decisions about which food to pursue based on their positions and potential risks. Additionally, we've introduced dynamic obstacles that appear and disappear, creating temporary barriers that the snake must navigate around. These elements make the environment richer and more dynamic, providing a robust testbed for our Q-learning algorithm to develop and refine its strategies under varying and unpredictable conditions. Turning to the design of our AI agent, which is the snake itself, the agent's decisions are driven by the state of the game. The state is defined by several factors: the position of the snake's head relative to the walls, the position of the nearest food item, and the immediate direction of the snake's movement. This comprehensive state representation helps the agent understand its current situation within the game environment. The snake can perform 4 actions: move up, down, left, or right, corresponding to the possible directions in the grid-based environment. The choice of action at any given time is determined by the Q-learning algorithm, which uses the current state to look up the best action in the Q-table. The reward system is designed to encourage survival and strategic playing. The agent receives positive rewards for each food item it consumes, which not only increases its score but also its length. Conversely, it receives negative rewards for colliding with the walls or itself, which leads to the end of the game. Additionally, small penalties are imposed for non-productive moves, where no food is consumed, and no collision occurs. These penalties discourage aimless wandering and promote efficient, goal-directed behavior. Through this design, the snake learns to navigate the game environment effectively, optimizing its path to collect food while avoiding hazards. Over time, the agent uses the experiences from each game iteration to update the Q table, refining its strategy to balance risk and reward optimally. In this project, we structured our implementation using 4 key Python scripts, each designed to handle specific aspects of the Q-learning application within the Snake game. This modular approach not only streamlined the development process, but also enhanced our ability to systematically test and refine the learning algorithm. Python file for Snake. This script is the backbone of our project, handling all game mechanics. It manages the movement of the snake, the generation of food items, and checks for collisions, thus setting the stage for the Q-learning agent to interact with the game environment. Q-learning model file. At the core of our learning model, this script implements the Q-learning logic. It manages the Q table, processes the state inputs, decides the actions based on the current policy, and updates the Q values based on the rewards received after each action. Experiments file. This script automates the running of multiple game simulations under various parameter settings. It adjusts the Q-learning parameters like gamma, epsilon, and the number of episodes, running each configuration multiple times to gather data on the performance outcomes, which it then stores in a CSV file for further analysis. Python file for plotting experiments. After collecting data, this script takes over to visualize the results. It reads the data from the CSV file and uses graphing tools like Matplotlib to create visualizations that show how different parameters affected the learning outcomes. These visual aids are crucial for understanding the impact of each parameter on the agent's performance and for demonstrating the effectiveness of the Q-learning implementation. Together, these scripts form a comprehensive system that not only simulates and analyses the Q-learning process, but also provides clear insights into how artificial intelligence can navigate and master complex environments like the Snake game. In our study, we explored how different learning parameters influenced the performance of our Q-learning agent in the Snake game. We specifically looked at the effects of exploration rates, discount factors, and training durations. Epsilon values between 0.3 and 0.5 yielded the best performance, balancing exploration and exploitation effectively. For example, an optimal epsilon of 0.3 led to the highest average score of 35 at 17,500 episodes, while extremes in low or high epsilon values resulted in suboptimal outcomes due to insufficient or excessive exploration. Higher gamma values, such as 0.95, significantly improved long-term strategic planning, with the Snake achieving higher scores in extended training sessions up to 20,000 episodes. This indicates the importance of future rewards in the agent's decision-making process. Longer training periods consistently improved performance, underscoring the necessity for sufficient exploration of the game environment to refine strategies. Training for 20,000 episodes, for instance, led to notable improvements compared to shorter sessions. We observed performance peaks at specific settings, such as gamma of 0.9 and epsilon of 0.3, indicating optimal conditions for our game setup. Additionally, we found that increasing the number of episodes past a certain point showed diminishing returns, suggesting a plateau in learning. These results highlight the delicate balance required in setting Q-learning parameters and the potential for these parameters to significantly impact the learning outcomes and effectiveness of AI agents in dynamic environments. In conclusion, our exploration into Q-learning with the Snake game demonstrated that optimal exploration rates and higher discount factors significantly enhance agent performance. These findings highlight the potential of tailored reinforcement learning strategies not only in gaming but also in complex applications like robotics and autonomous systems. Despite its successes, the project's simplicity in the Snake game environment suggests room for applying these strategies to more intricate settings. Future research will focus on integrating advanced algorithms such as double Q-learning and exploring adaptive learning rates to tackle real-world complexities. Thank you for your attention. We look forward to furthering the boundaries of AI capabilities with these insights.